Good day everyone, I'm Raymond Buquis, and today I'll be talking about the op-amp instrumentation circuits and the instrumentation amplifier. Before anything else, you can refer to the corner note that I posted on eLearn so that you'll be able to follow all throughout the lesson. So we have discussed in class before what an op-amp is all about, and today we'll be tackling about its applications. A popular area of op-amp application is in instrumentation circuits. A few typical circuits will demonstrate how op-amps can be used. So I'll be discussing about the types of instrumentation circuits that deals with op-amps, and the following are DC millivoltmeter, AC millivoltmeter, display driver, and lastly the instrumentation amplifier. We'll start with the DC millivoltmeter. The following devices are required to build such millivoltmeter: op-amp, resistors, and a 0 to 1 milliampere meter movement. So here we have a figure that shows a 741 op-amp used as the basic amplifier in a DC millivoltmeter. Now if you're wondering what 741 op-amp means, it is monolithic integrated circuit comprising a general purpose operational amplifier. The number 741 indicates that this operational amplifier IC has 7 functional pins, 4 pins capable of input, and 1 output pin. A meter movement is an electronic device that the indicator will deflect proportionally according to the current going through. Take the 0 to 1 milliampere meter movement for example. 0.5 milliampere current will result in half-scale deflection, while 1 milliampere current will result in full-scale deflection. Therefore, the essential to build a millivoltmeter is to convert the voltage into the current, and then this current is delivered to the meter movement. As a result, the meter reading on the meter movement can represent the voltage. So we have this formula of the circuit transfer function. The absolute value of I0 divided by V1 is equal to RF divided by R1, then multiplied by 1 over Rs. In this case, the feedback resistance is just equal to the input resistance, which is 100K. So 100K divided by 100K multiplied by 1 over Rs, where Rs is 10. So 100K over 100K, we can cancel that out, and we are left with 1 over 10. So we have 1 milliampere over 10 millivolts. So changing the resistance can adjust the scale factor. Another example of an instrumentation circuit is the AC millivoltmeter as shown in figure 2. The circuit transfer function is the same as the DC millivoltmeter, except that in this situation, the signal that is being handled is an AC signal. So the meter indication provides a full-scale deflection for an AC input voltage of 10 millivolts, whereby an AC input of 5 millivolts produces a half-scale deflection with a meter reading interpreted in millivolt units. So, same as what we had earlier, RF and R1 are just the same, so 100 kilo divided by 100 kilo multiplied by 1 over Rs, where Rs is 10, and this 2 can be cancelled out, so we are left with 1 over 10, so 1 milliampere over 10 millivolts. So both DC and AC millivoltmeter has the same circuit transfer function, but they do actually differ in signal handling. Moving on to display driver, op-amp circuit can be utilized to drive the lamp display or LED display. Display driver is a circuit R component used to control another circuit R component such as lamp display or LED display. When an inverting input to circuit in figure 3 goes above the inverting input, the output on terminal 1 goes to positive saturation level near the plus 5 volts in this example, and the lamp is driven on when transistor Q1 conducts. As shown in the circuit, the output of op-amp gives 30 milliampere of current to the base of the transistor Q1, which then drives 600 milliampere of current through properly selected transistor with B that is greater than or equal to 20. capable of handling that amount of current. Another circuit in figure 4 shows op-amp circuit which can supply 20 milliampere to drive LED display when non-inverting input goes positive compared to the inverting input. So, moving on to the last topic, the instrumentation amplifier. A circuit giving the output based on difference between two inputs times a scale factor. Potentiometer is provided to allow adjusting the scale factor of the circuit. While 3 op-amps are utilized, a single quad op-amp IC is all that is essential, other than resistor components. So the instrumentation amplifier is suited perfectly for detecting and amplifying a small signal deviation when superimposed on one or the other two of much larger and otherwise identical signals. An instrumentation amplifier consists of 3 op-amps, as shown in figure 5. First, we have to examine the circuit configuration of the first 2 op-amps. We can start by examining the pair of input op-amps. For op-amp 1, Vp is equal to Vn1, which is also equal to V1 because of op-amp voltage constraint. Therefore, we can also say that Va is also equal to V1 since Va is equal to Vn1. Similarly, for op-amp 2, we can say that Vb is equal to V2. Since both In1 and In2 is equal to 0, and this is because of op-amp current constraint, we can say that I2 is equal to Vb minus Va over R2, which is also equal to V2 minus V1 over R2. We can solve VO2 minus VO1 by multiplying I2 to the sum of R1, R2, and R3. So, by substituting the value of I2, we get VO2 minus VO1 is equal to R1 plus R2 plus R3 over R2 times V2 minus V1. So we can set R1 plus R2 plus R3 divided by R2 by G1, where it is the circuit gain of the first stage, which includes op-amp 1 and 2. The third op-amp is a difference amplifier that amplifies VO2 minus VO1 by a gain factor G2 given by G2 is equal to R4 over R5. Therefore, to get VO, we multiply G1, G2, and V2 minus V1, so we get VO is equal to R1 plus R2 plus R3 over R2 times R4 over R5 times V2 minus V1. So, to simplify the circuit and improve precisions, all resistors, with the exception of R2, are often chosen to be identical in design and construction, thereby minimizing deviations between their resistances. So if we set R1, R3, R4, and R5 to R, the expression VO reduces to VO is equal to the quantity of 1 plus 2R multiplied by V2 minus V1. So we have R here and R, so that will be cancelled out, and R and R, so that makes 2R. So over R2, then we separated R2 over R2, then that makes 1. In that case, R2 becomes the gain control resistance of the circuit. Its value relative to R sets the gain. Thus, the instrumentation amplifier is a high sensitivity, high gain deviation sensor. So here we have an example problem of solving in DC millivoltmeter. We are given with this figure and we are asked to calculate the output current I/O. So using the formula that we have discussed earlier, I/O divided by V1 is equal to RF over R1 times 1 over Rs. So we are asked with I/O, so we need to multiply both sides by V1 in order to get V1 in the left hand side. So we have this equation. I/O times V1. So I/O is equal to RF over R1 times 1 over Rs times V1. So by substituting the values, we get IO is equal to RF. We have RF 100 kilo. So 100 kilo. We have R1 200 kilo ohms. And we have RS 10 ohms. And V1 we have 10 millivolts. So by calculating this, we can actually get IO. Then IO is equal to 0.5 milliamperes. The second problem is instrumentation amplifier. We are given with a circuit and we are asked to solve for VO. So using the formula, so since R4 and R5 varies, we use the formula VO is equal to R1 plus R2 plus R3 divided by R2 times R4 over R5 times V2 minus V1. So by substituting all the values, we can actually get VO. We have R1 and R3, which is 5 kilo ohms. So 5 kilo ohms, 5 kilo, 5 kilo. We have R2, 1 kilo ohm. So 1 kilo and then another one. And both R4 and R5 are 10 kilo ohms. 10 kilo and then another 10 kilo. And we have V2 as 1 volt and V1 3 volts. So 1 minus 3. So by calculating this equation, we can actually get VO is equal to negative 22 volts. So that concludes my report. Thank you so much for listening, and I hope you guys have a great day.